Okay, so now I want to move in and talk about the case study. This is the third case study you're going to do. Unlike the previous two, this one you're going to do it on your own. So it's not a team-based case study. And this one we're going to be focusing on travel time-based performance measures. So it fits very well with the personal transportation topic from Chapter 5 of the e-primer. This tells you what we're trying to accomplish here. Is in particular, we're going to focus on travel time performance metrics. That's has a huge level of interest these days, and both in terms of the travel time itself and the travel time reliability. And we'll talk about the importance of that. We'll look at some of the basic principles behind those metrics. Look at actually how you could compute them with a data set, and talk about how people actually use these performance measures. Oops, I went the wrong way. Okay, and again, this is performance measures are gaining popularity in all fields, quite frankly. And a lot of the idea here is that we have to measure the quality of service, the quality of our systems in order to maintain them and to improve them. And in many ways in the past, transportation has been a little bit lax in terms of having really well-defined performance measures. In many ways, because it's such a complex system, it's hard to boil all the information down to a small metric. But the focus here is to try to do just that. Here's some examples from a WMATA, which is the provider of transit services in the Washington, D.C. area. You see here some of the things that they do: on-time performance, escalator availability, all these sorts of things. Other examples here, this is from the Maryland State Highway Administration. So we're going to focus here in this case study on travel time and travel time reliability. So obviously travel time is the time it takes to travel from point A to point B. The reliability is a measure of the impact of non-recurrent congestion. In other words, how impactful are crashes, special events, things you don't normally have, and how much essentially can your trip vary from day to day in terms of travel time, which we're finding is really important to travelers. If you live, for example, in the Washington, D.C. area, or Houston, or Atlanta, or Los Angeles, you will face some level of congestion on commutes. What people find really troubling and difficult to deal with are the impact when that delay can change dramatically from day to day, because then you have to essentially plan for the worst case every day, and you lose a tremendous amount of time. So there's a lot of value in having more reliable travel time. Okay. This is essentially what I just talked to you about, so I won't restate it. But these are really important travel time, really important metrics in terms of the user satisfaction, primarily from a highway user perspective. We can do a really good job measuring the travel times these days because we have so much data, and particularly we get so much data from third-party vendors. The data you're going to look at here in this case study is from a company known as INRIX, which basically has a contract with the I-95 Corridor Coalition, which is a group of states all up and down the East Coast, to provide travel information to support ITS applications. I can tell you that VDOT in our laboratory here at UVA, we work with this data on a regular basis. So this is data that is actively used today in the industry. This data can come from sensors. It can come from a third-party provider like INRIX, who does this as part of their business, etc. So this class is not a statistics class, and I am assuming that you have basic knowledge of probability and statistics coming into this class. If you don't, please let me know. We can talk a bit more about that. But just as a refresher, we're looking at using the probability density function and the cumulative distribution function, using these tools to derive the travel time metrics. And again, the PDF is basically the likelihood that a variable will assume some given range of values. A cumulative distribution function is a probability that a variable will assume a value less than or equal to a given value. So these are basically looking at the same distributions, just different ways of looking at the values. So what you see here on the top right are a series of, in this case, normal distribution PDFs with different means, which is the center of the distribution, and different standard deviations, or essentially the variability of the data. The blue curve obviously has quite a bit of variability, whereas the red curve has very little. These same PDFs are now plotted in terms of their cumulative distribution function on the bottom, on the right on the bottom. And again, you see here for the red PDF, you have nearly a vertical line for your cumulative distribution function because all the data is in that very narrow range. And you see all of the CDFs are moving up towards a value of 1 because at the maximum value, everything is less than or equal to that particular value of the variable. So again, thinking of it from a travel time perspective, if I have two distributions, the lighter color distribution here, I have a mean travel time of 3, a standard deviation of 0.2 minutes. The second one, the darker one, also has a mean travel time of 3 minutes, but in this case I have a standard distribution of 0.5 minutes. So, and they are different distribution models, but you can see these are very different experiences for travel. You're going to have much more variability with this darker PDF than you would with a lighter PDF. And you see that here when you look at the cumulative distribution functions. There is relatively little variability for this lighter distribution. So, how do we use this for our performance measures? It's really pretty simple, and in fact, we've used these percentiles quite a bit in transportation already. So this is something that we can use the data we get from travel time information providers, from our own sensors, to derive travel time metrics. So the first metric is the travel time index, and that is simply the order of magnitude that the free flow travel time increases during the time period the travel times are collected. So for example, during rush hour. So if I look at the average during the peak period and divide that by the average during the free flow period, that will tell me essentially what my travel time index is. So again, we don't use travel time by itself because that would then be dependent on the length of a section we're looking at. We want to try to make this metric to be independent of the geographic size. Oops, sorry. So the less a roadway's TTI is, the more or less the road suffers from concurrent congestion. So that would be less. Again, the higher the travel time index, the more congestion. The more congestion you have. The next question is, if the free flow travel time on your commute to work is 15 minutes and the rush hour TTI is 1.33, how long does it take you on average to get to work during rush hour? In this case, again, I have a 15-minute free flow travel time. This will be 33% greater, so now my total travel time during the peak period is 20 minutes. A planning time index is another metric, and this one is trying to capture essentially how much variability I have in my travel time. So this is a multiplier that can be applied to the free flow travel time to get the travel time needed to be at the 95 percentile of travel times. In other words, how much extra time do I need to give myself to make sure that I'm on time 95% of the time? So this one really compares how the worst travel times are and how much this non-recurrent congestion is really influencing things. So again, the greater a roadway's PTI is, the less reliable the roadway is. And can a roadway have a relatively high PTI and a low TTI? Yes, it can. It's particularly if you have a long right-hand part of your tail. You have a lot of a lot of samples where you have high delay because of an incident, for example. So you certainly can have a low TTI. In other words, during peak period, I have relatively little recurrent congestion, but I have big problems with non-recurrent congestion. So here's an example. So in this case, we're going to use a 50th percentile travel time for calculating TTI. We're going to assume the 50th percentile is the kind of the average time you find during a peak period. So in this case, if you look at this plot, our 15th percentile is at about right in here, about 16. Let's see, right about here, 16. If our 50th percentile is over here at about 37. Our 95th percentile, way up here, is going to be at 56. So now my PTI is simply going to be my 50th percentile divided by my 16th percentile, or 37. My TTI, my travel time index, my normal delay is going to be 37, which is my percentile, my 50th percentile value, divided by 16, which is my 15th percentile value. So that gives me a value of 2.3. My planning travel time index is going to be my 95th percentile, or 56, divided by my 15th percentile, which is 16. And so that gives me a value of 3.5. So in this case, for this particular set of data, for this particular roadway, I have a travel time index of 2.3, a planning time index of 3.5. This road has some significant challenges in terms of travel time, and that I have some, quite a bit of delay during normal periods, and I can have, a significantly varying amount of delay based on non-recurrent congestion. So where does this data come from? Again, we said earlier it comes typically these days that you're purchasing it from a travel time data provider. It can come from sensors that a DOT itself has deployed, but in this case we're going to use a third-party vendor software. This is what your data set will look like for the case study. You'll have a TMC code. A TMC code is basically the way the travel time community segments roadways by beginning, ending location, and by direction. So it's just basically it's a standard for geographically capturing a portion of a directional roadway. You have a time, you'll have their average speed that they derived, and then you will get other information. They give you the average speed and the travel time which they derive. The confidence score and C-value are things that they use in terms of how confident they are in the data. We're not going to use that right now. If you were going to the I-95 Corridor Coalition's website, you would download data this way. We're not going to do that now since we're not using that for this case study, but it's important to note that one of the things that DOTs are trying to do is get this data out to users. So this is an example of how you can get to this data. So now basically what you want to do is you want to create your percentiles. So you can have a column that will state the percentiles. I'll often do it in 5% levels. And create that, and then I can use this particular function or command, which will calculate the percentiles based on the selected array. In other words, the actual set of data. And it'll be based on, again, you'll say it is a fifth, 5%, 10%, what have you. So I could use this to create these percentile values and then use those directly in my travel time index calculations. So again, in this case, you see I've done that, and for my TTI, I simply am going to divide the 50th percentile, which is 63, by my free flow, in this case, which is 60. So what I have here, that will give me what my actual TTI is in this case, which are 1.03. So this case is great. We have very little variability. The peak period congestion is pretty much the same as congestion off-peak. Okay, so you will have, for the case study, 5 locations on a fictitious freeway, and you'll have 5 data sets with travel time data from those locations. And what we're asking you to do is basically compute TTI and PTI for these locations, and then basically analyze that and interpret that and tell us what this means in terms of the congestion in these locations, the level of priority to address it, things of that nature. So again, we can have things like this, which talk about the actual congestion. You could do the same thing in terms of travel time index too. VDOT, you're looking at Maryland's here. Actually, the Smart Travel Lab here at UVA, we've created lots of plots like this, and many of them are time series animations that show this sort of data for freeways in Virginia based on the data that VDOT has access to. So then we can use this information to look at, are there segments that are unreliable and need attention? This case is in Maryland a couple of years ago. Justifying investment, things of that nature. So again, the idea of these metrics is to take this large amount of data, compile it into smaller, easier to understand metrics that can drive decision making. That's what you're going to do for the case study. You're going to do just that for 5 locations, and then take all this information and try to make some sense out of it in your write-up. Okay, so with that, I think that gives you the introduction you need to really get going on Unit 3. As always, if you have questions, concerns, please feel free to email me, call me, stop by. I'm happy to help you. So I will close now. Thank you.